This video covers discrete random variables, and we will be discussing the probability distribution function and expected value. So, in probability, if we were to roll one die, and I were to ask you what's the probability of rolling a number that is odd, you would say 3 out of 6, which is 1/2 or 0.5, because there are 3 sides that are odd, 1, 3, and 5 out of 6 total sides. But what if we rolled 5 dice instead? What would be the probability that all 5 of them come up odd? Or what if we rolled 4, or rolled 5 and asked, what's the probability that 4 of them come up odd? So that begins to make things a little bit more complicated. And that's where random variables come in. A random variable is the numerical outcome of a probability experiment. So if I were to roll a die, the numerical outcome of the die I rolled could be a 1, or a 2, or a 3, or a 4, or a 5, or a 6. So it varies, which is why we call it a variable. It's also random. You don't know what's going to come up. Now, we can also call the specific one that I just gave as an example a discrete random variable. If you think back to the word discrete when it was introduced, it was defined as data that could be counted or listed. So things like the number of pencils in your backpack, you can count those, 1, 2, 3, 4, 5. So a discrete random variable is a random variable whose possible values can be listed. So the numerical outcome of a probability experiment where the numbers can be listed, such as when we roll a die, you can get a 1, a 2, a 3, a 4, a 5, or a 6. Or the number of heads when you're flipping a coin 10 times, you could get no heads, or 1 head, or 2 heads, or 3, or 4, or 5, or 6, all the way up to 10. Now, with our new terminology, we also have some new notations. Random variables are denoted with the capital X. That represents all of possible outcomes. But when we get specific to a specific outcome, values that the random variable can take on are denoted with lowercase letters, a lowercase x. So when we want to know what's the probability that you're going to flip a coin 10 times and it come up heads 9 times, you would write it as the probability of 9, with 9 in the middle of the parentheses. In this case, we're using the lowercase x because that x represents all the random variables that are possible, all the values that the random variable can take on. So what you see here is a probability distribution table. It is very similar to a relative frequency distribution table that you have seen before. And what it is it lists all the possible random variables, all the values that the random variable could take on. In this case, if we roll a die, the numerical outcomes, the discrete numerical outcomes that could come from that are rolling a 1, a 2, a 3, a 4, a 5, or 6. And then for each of those possible outcomes, each of those random variables, you list their corresponding probabilities. So the probability of rolling a 1 would be 1 out of 6. The probability of rolling a 2 is 1 out of 6. The probability of rolling a 3 is 1 out of 6, so on and so forth. And so that is a probability distribution. So you basically list all the possible random variables, all the possible numerical outcomes that could happen, and then list their probabilities. So let's look at example 1, rolling 2 dice. Roll 2 dice and let x be the sum of the values. Build the probability distribution function for this experiment. So the sum can be, sum means add, okay? So here we have 2 This is 3, 4, 5, 6, 7. So I'm getting those by adding the numbers that we get together. So you could roll a 1 and a 1, or a 1 and a 2, a 1 and a 3, a 1 and a 4, a 1 and a 5, 1 and a 6. And if I add those two die together, like here, 1 plus 1 would be 2, or here, 1 plus 2 would be 3, 1 plus 3 would be 4, so on and so forth. And so now you can see that I have filled in all of the sums of all of the possible numbers you could get if you rolled 2 dice. And the sum can be anything from 2 to 12. Okay? So, to make a probability distribution, the possibilities for the sums were 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So the probability of the sum of 2, so let's go back here, there's 1, 2, out of, there's a total of 36 sums. There's a total of 36 here. If you count up, that'd be 36. So 1 out of 36. Right here, 1 out of 36. Now, 3, 1, 2, 2 out of 36. 4, 1, 2, 3, 3 out of 36. 4, well, we just did 5, 1, 2, 3, 4, 4 out of 36. 6, 1, 2, 3, 4, 5, 5 out of 36. Hopefully you're seeing that there's a pattern here. And 7 goes all the diagonals. See all the diagonal? Each one of the sums is a diagonal. And you can count it pretty easily. 7, 1, 2, 3, 4, 5, 6. So 6 out of 36. 8 goes back down to 5 out of 36. 9 is 4 out of 36. 10 is 3. 11 is 2. And 12 is 1 out of 36. And then you'll see here what we did is we divided each of these values, 1 divided by 36, and we translated it into its decimal form, 0.0278, rounded to 4 decimal places. 2 out of 36 is 0.0556, so on and so forth. So we've just created a probability distribution for rolling 2 dice and the sum that you would get. Example 2, flip a coin twice. Flip a coin twice and let x be the number of heads. Build a probability distribution function for this experiment. So why don't you pause the video and see if you can create the sample space and use that to come up with your probability distribution table. Remember, the random variables have to be numbers. So it's the number, x is the number of heads. So think about how many heads you could get. You can get either, you can flip 2 coins and get no heads, or you can get 1 head, or you can get 2 heads. So pause the video and try it. Alright, so as I said, you can get 0 heads, 1 head, or 2 heads. So let's see how the sample space looks. You can flip 2 coins and get a heads and a heads and a tails and a heads, or a tails and a tails. So that's 4 outcomes. So for the probability distribution table, the 4 total, that's going to help us with our probability, but as far as our random variable, there are 3 possibilities as far as getting the x being the number of heads. So you can get 0 heads, that would be flipping 2 tails, getting 1 heads, or getting 2 heads. So to find each of those corresponding probabilities, no heads would be 2 tails right here. So that's 1 way out of 4, which is 0.25. 1 head, I can either flip a head and a tails, or a tails and a head. So that's 2 ways out of 4, or 0.5. And then the probability of 2 heads, there's only 1 way to do that, heads and a heads. So that's 1 way out of 4, which is 0.25. So there we've listed all the random variables and the corresponding probabilities. Take a look at this example. There are 5,000 undergrads at college. The following frequency table describes how many of them are taking a given number of courses. If x is the number of courses that a randomly chosen student is taking, find the probability distribution for x. So these numbers here, 1, 2, 3, 4, 5, and 6, are your random variables. So those you've already got listed. Now you just want to find the probability of each. So pause the video and see if you can try this. Okay, so to find the probabilities, you need to add up all of these numbers and get a total, which the total should be 5,000. Okay, so then you would take each of these numbers. What's the probability that you choose a student that's taking one course? That would be 478 out of 5,000. The probability of 2 courses, 645 out of 5,000, so on and so forth. So your resulting probability distribution, dividing each of these frequencies by 5,000, gives us the following. And what you'll notice is that these numbers are the same thing we would get for relative frequencies. Think about how you find relative frequency. You take the frequency and you divide by the total. For probability, you take the number of ways something can happen and you divide it by the overall total in the population here. So there's 5,000 undergrads, so this would be 478 out of 5,000. The exact same thing we get for relative frequency. So here's a couple properties that you need to note. They're very important. 2 rules for probability distributions. The first one is the same rule that we have for any probability. Probabilities are always between 0 and 1 inclusive. So we've got the little equal sign here because it means that 0 can be a probability and 1 can be a probability, but you can't have negative probabilities to the left of 0. You can't have probabilities greater than 1. So probabilities are always between 0 and 1. So that property is a rule for a probability distribution, but it's also a rule for all probabilities. Now this probability rule is specific for probability distributions. The sum of all the probabilities in a probability distribution add up to 1. If you pause the video and go back to all of the probability distributions that we've looked at or done in an example, all of those probabilities will add up to be 1. Now, the only time that it doesn't happen is occasionally when you do round, your probabilities, let's say to 4 decimal places. You might get a probability like 1.0003, and that has to do with the rounding. But if you gave the exact results, let's say in fraction form, and added them together, they would add up to be 1. Basically, if you look at this, this pretty much rounds to 1. Another thing you could possibly get is 0.9997. That would round to 1 as well. So just be mindful of that when you're adding and you're trying to check to see if this property is upheld, to see if something's a probability distribution, or checking to make sure you have all the correct probabilities in your distribution. You could get a number close to, super close to 1, like this. Now, if you get something like this, 1.25, that's way too high. That's not close to 1. So if it's super close to 1, you can tell it's because of rounding. That's okay. But otherwise, you should get 1. Alright, we're going to stop the video here, and we're going to pick up with example 4 supermarket customers and part 2 of discrete random variables.